Thank you so much for joining this lesson. We'll be discussing physics paper 1, both section A and section B. Remember to subscribe and to share this link with your friends. Number 1 of this paper. The figure below shows a Bunsen burner. So we can see a Bunsen burner. The main parts have been outlined very well. Then the examiner demands we explain briefly how it works. The point is that when the gas tap is opened here, you see the gas supply. So the gas enters the barrel at a very high speed. The gas enters the barrel at a high speed. At a high speed, creating a low pressure zone. A low pressure zone. Look at that. The gas enters the barrel at a high speed, creating a low pressure zone. This is according to the Bernoulli's effect. The greater the velocity of a fluid, the lesser the pressure it exerts. So now atmospheric pressure in the outside. Atmospheric pressure from the outside now being greater, pushes air in, through the air hole. So once air has been drawn in now, because of the pressure difference, gas is moving at a very high speed inside the barrel. Atmospheric pressure now greater, pushes air in. Because it is now at a greater pressure. Then now the mixture of air and gas ignites. This is now what burns, and hence the Bunsen burner functions. So that is the simple functioning of the Bunsen burner. This is the best school online. Please make sure that you invite somebody. As we continue looking at these physics explanations, it's good you have your friends on board so that they may also benefit from whatever we are covering here. Look at number 2. The figure below shows glasses resting on an incline or an inclined plane. One glass is empty and the other is filled with water. State which glass is more unstable and will topple. Then you explain. More unstable. Look at that language. When they are positioned like that, they are both unstable, but one is more unstable than the other. Therefore, it is the glass with the water. The glass with the water. The water raises the position of the COG. The position of the center of gravity. COG, it's good you write in full when you're answering. The center of gravity, lowering the stability. Lowering the stability. Since the line of action will pass outside the base. Outside the base. Remember, the area of the base and also the position of the center of gravity are usually the two main factors that affect the stability of an object. So even though the glasses are having some good base, discover that the center of gravity, when acting here, shall pass through the base, and hence the glass will remain stable. But at this point, the position of CAG is raised, and the line of action is likely to be outside the area, the base, and the glass is going to topple over. It shall topple over. So it's about the line of action passing through the base or not through the base. Number 2, this is a paper which is very involving, well thought out questions with a lot of application. And I would encourage learners and students to follow with a lot of keenness. You are actually required to have a lot of details in physics as you respond to this paper. You can't just rush to some of the science questions like physics. You have to have your details in order. Because now in number 3, we are told that this is a diagram of a greenhouse used to grow crops under controlled conditions of temperature. Explain how the greenhouse achieves relatively higher temperature than the outside. It's good for you to know that radiant heat is able to penetrate through this material. So you can say that radiant heat, which has short wavelength, penetrates the glass. Radiant heat or infrared. Radiant heat penetrates the material, penetrates the glass, yeah, and gets absorbed by the plant. And gets absorbed by the plant. Like that. So once the plant has absorbed now, it will emit radiant heat, which is a bit different now, with a longer wavelength and hence less energy. So the plant in return now emits radiant heat of longer wavelength, meaning a lesser energy, unable to penetrate the glass to the outside. So you see, radiant heat from the environment penetrates the glass. After the plant has absorbed it, the energy that the plant shall emit will have longer wavelength, or rather less energy. Hence, it will be unable now to penetrate the same glass to the outside. When we talk about longer wavelength, remember energy is usually given by HF, and we can also say that energy equals to H, and instead of F, can have velocity over lambda. So lambda is inversely proportional to energy. So the greater the wavelength, the lesser the energy produced. So now the plant emits energy of longer wavelength, meaning lesser energy. Hence, can't penetrate to the outside. So now higher temperature is able now to, the temperature of the greenhouse now is increased. The temperature of the greenhouse is hence increased. Of the greenhouse is hence increased. Hope you've gotten it right. It's a very good question. Looking at number 4, as I mentioned something about our programs here, we're calling it the one-term ahead program for the December holiday, November-December holiday, from the 20th of November to 12th December via Google Meet. We shall have very interactive classes. We'll be covering the 2026 Term 1 work, and we'll be targeting junior schools and senior schools. We have acquired specialists from all learning areas and all the subjects. Please be rest assured that you'll be getting the best from the best in the country. So we have the best teachers. Please find time. Organize a date with shifting grades, and you shall not regret. So please make arrangements. Our consultation line is already attached on the wall, 0704153366, and you will not regret joining us. So those who are continuing, by the time you'll be going to your next level in 2026, you shall arrive there when you are one term ahead of the others. Number 4, the diagram below shows a solar heater that is used to heat water for domestic use. You have a glass window, and of course, you know why it's made of glass. Then you have cold copper pipe, then some cold water, but towards the storage tank, you can see it's warm water. States Roman 1, why copper pipes are used. This is because copper is a good thermal conductor. Copper is a good thermal conductor, or rather a good conductor of heat. Why copper pipes are blackened? They are blackened for maximum absorption of radiant heat. For maximum absorption of radiant heat. You know very well that substances absorb radiant heat, but when they are black, absorption rate is usually increased as opposed to shiny substances. Why copper pipes are coiled? They are coiled to increase surface area for absorption. To increase surface area for absorption. Yeah, to increase surface area for absorption. Imagine if the copper pipe was just very straight, that surface area would be highly limited. So to avoid all that, we have it coiled to maximize on the surface area for maximum absorption of radiant heat as the pipes carry some water. Number 5, the diagram below shows a porous pot that has hydrogen gas trapped around with a beaker. So we have a beaker, the gas jar that you can see. We have air, we have the porous pot, then hydrogen gas is in there. State and explain the observations made in the U-tube. That's where observations are being made, strictly there. You know that hydrogen gas is less dense, so it's able to diffuse very quickly. It's lighter, or rather, less dense. So the less dense hydrogen diffuses through the porous pot. And after it has diffused through the porous pot, now it shall enter the U-tube, and water on the, this is water. So water on the left arm shall go down as water on the right arm rises up. That's one of the observations. There might be others, but you can say that. And by the way, we can also see, because of the hydrogen gas, we can also observe some bubbling. Yes, some bubbles coming out. So you can say that water level on the left arm of the U-tube goes down and rises on the right arm. This is because the less dense hydrogen diffuses through the porous spot into the U-tube. Diffuses through the porous spot to the U-tube. So this is about diffusion. Hydrogen is highly concentrated between the gas jar and the porous spot. So it has to diffuse where there is air. Yeah, it has to diffuse. And by the way, as it pushes air, remember it is hydrogen to enter here and push the air through the tube. Hence the bubbling and also the change in levels of liquid. Yeah, like that. Number 6. The figure below shows the velocity time graph of two identical spheres released from the surfaces of two fluids, A and B. Then we have the curve for A and the curve for B. Show on the diagram the terminal velocity of the sphere in liquid B. So terminal velocity is the velocity where now the sphere has fully accelerated. So this is velocity terminal. That is the level of velocity that we call terminal velocity when the body has fully accelerated. With reason, you state the fluid with a higher viscosity, and that is going to be A. You see, the maximum velocity attained is smaller in A. That means A is resisting motion more than B. It has lower terminal velocity. It has lower terminal velocity. Technically, this particular liquid, fluid, is the one that is resisting velocity more. You know, the ability of a liquid to resist motion is what we call viscosity. So it has a higher viscosity. It has a higher viscosity. Number 7, water flows through a horizontal pipe of varying cross-section area as shown in the figure below. We have the region A, region B. You can see the different cross-sections. Velocity of water in pipe A is 2 meters per second. Determine the velocity of water in pipe A. This now according to the equation of continuity, which says that cross-section area times velocity equals to cross-section area times velocity on the other end. That's why the smaller the cross-section, the higher the velocity to counter. You know, this is the rate of flow now. So we'll say that 100 times 2 equals 2. On the other side, we got 60 times unknown velocity. So we can remain with velocity 2. We divide through by 60. When we perform that division, we get 3.33 meters per second. Meters per second, like that. So that's the velocity. State one assumption you've taken in the part A above. For you to compute that, or for you to apply the equation of continuity, then this equation is obeyed by a liquid which is assumed to be having a steady flow, the fluid being non-viscous, and also being incompressible. So the fluid is incompressible. The fluid is incompressible. Incompressible with the steady flow and non-viscous. So those are the 3 assumptions for fluid to obey the equation of continuity. Number 8, we can read it together that a machine raises a mass of 20 kilograms through a distance of 0.2 meters when an effort of 100 Newton is moved through a distance of 0.32. Determine the velocity ratio of the machine. Velocity ratio, VR, of a machine is given by distance. The effort goes through, out of the distance the load goes through. So effort goes through 0.32. The load goes through 0.2 meters. So we can carry out this division and we get exactly 1.6. No units for velocity ratio since it's a ratio of two distances. A very simple question. I would also like to challenge learners to read questions with a lot of carefulness and also get to understand what the examiner demands. Yeah, let people get to understand the demand of an examiner, because looking at this question, we've been told to compute the velocity ratio, yet we've been given mass, which will not be required. We've been given the effort required, and it's not a requirement for velocity ratio. You might find somebody struggling to make sure that they apply this 20, struggling to ensure that they apply this 100, Yet, according to the demand statement, we only need the distances and we'll be there. So let people not over struggle so much. At 9, an object of mass 0.5 is tied to a rope and whirled in a horizontal circle. Radius of the string is 2 meters and the velocity is 8 meters. Determine the tension on the string. Now, when a particle is moving in a horizontal circle, it's good to know that tension is also equal to the centripetal force. And this is usually given by mass times velocity squared out of the radius of the path. So 0.5 times 8 squared out of the radius of the path, which is 2 meters. This now computed will give us exactly 16 Newton as the tension on the string. So tension on the string is usually provided by the centripetal force, and we know the formula for centripetal force. Look at number 10. The figure below shows a mercury manometer connected to a gas tank. The gas tank there, the gas applies some pressure until it raises a column of 26.4 centimeters, and it's a mercury manometer, meaning that the liquid inside here is mercury. State the pressure of the gas. State, the word is state. So here, to state this, you can write it as 26.4 centimeters of mercury. Those are recommended units of pressure. You can also give it as 264 millimeters of mercury. Now, in case you had been told to find the pressure in SI units, then you would end up converting all these to Pascal or rather Newton per meter squared, whereby you will say now pressure equals to height times density times the value of gravity. Then now from here we can say that the height supported is 0.264. The density of this liquid is 13,600, being mercury. Then we multiply by 10. Then you compute now the pressure in pascals. So the pressure can still be computed in pascals depending on the level of mercury which has been supported. The reason why we are saying that the pressure is equal to the column here, we just take pressure at the same level. We usually say that when pressure is at the same level for fluids, it's usually equal. Therefore, at A and at B, as I indicated them here, pressure must be equal. At A, it's due to the gas, but at B, the pressure is due to the column of mercury, which has been supported at that level. Bearing in mind that above the mercury thread, we are only having a vacuum. So no pressure exerted at that point. This is a vacuum. Yeah, so you're supposed to understand such a setting of items. Two glass slides are dipped in water and put in contact. It is observed that the glass slides stick to each other. Explain this observation. The reason why they stick together is because there is, first of all, water, which is a very different molecules. Then these molecules of water and the glass are usually attracted together using what you call adhesive forces, now that the molecules are different. So the adhesion between glass and water is usually greater than the cohesion between the glass molecules, than the water molecules themselves, making it very possible for the glass slides to stick to one another. So you can say that the adhesive force between the glass and water is greater than the cohesion between water molecules. So that difference in the strength of the process is what brings the attraction of the glass slides. They are both attracted to the water, which is obviously now between the two. So water enters between the two, and they are both attracted to the water, which is in between, making the glass slides to be strongly attracted to one another. Section B of this. So if you are careful, you will learn a lot from these particular presentations. As we transition to section B, allow me to remind you of our program here, whereby airtime can be attained from your M-Pesa to any network. Safaricom, Airtel, Telcom. You just go to your M-Pesa, Lipa na M-Pesa. The pay bill number is already attached here, 737,356. Then the account number is the phone number that you're purchasing the airtime for. After you enter the account number, which is the phone number and can also be the phone number of a friend, you proceed to enter the amount, you complete the transaction, then the airtime is reflected instantly to your phone. Number 12, the figure below shows a tape after passing through a ticker tape timer operated at a frequency of 50 Hz, moving in the direction shown. Looking at the arrow, there is a direction there, implying that this particular ticker tape is decelerating, because look at the initial dots between P and Q. Within the same interval of time, the dot is bigger, but between X and Y, the dots are having a very small distance between them, showing that within the same time, a shorter distance is being covered. So there is a decrease in the velocity. But let's get to the setting of the questions now. Velocity on section PQ. One, there's something we're supposed to find even before we proceed to the questions. Now that frequency has been given, what about periodic time T? Periodic time is 1/f, meaning that 1/50. So that you know the time between one interval and another. This gives us 0.02. 0.02 seconds. That is the periodic time. Therefore, a distance of 5 is covered within 0.02, meaning that the velocity between P and Q shall be distance of 0.05 out of time. This now gives us 2.5 meters per second. I converted the distance, you can see. The velocity on section XY. Velocity on section XY again, we go to the distance out of 0.02. Now the distance is 0.01 because that's 1 centimeter, right? Then now 0.01 divided by 0.02, giving us 0.5 meters per second. You see now, velocity has decreased, meaning that the tape is decelerating. Roman 2, the force causing the change in the velocity, given that the body pulling the tape has a mass of 0.5 kilograms. We know that force is usually given by MA. This is the force that you need now. But before then, let's talk about acceleration of the ticker time. Acceleration is given by final velocity minus initial velocity out of time. If we are to substitute this now, we shall talk about final 0.5 minus an initial of 2.5 out of the time taken, 0.02 seconds multiplied by, let's get back to our tape now, and we count. We usually say that in between the first and the last regions, we count the number of intervals as they are. So this is 1, 2, 3, 4. We have 4 intervals. Then within the regions, we pick half the number of intervals. So we have 1, 2 intervals. So 2 intervals divided by 2 gives us 1. So we talk about 5 intervals now. So 0.02 times 5, like that. So let me compute. I'm getting negative 20 meters per second squared. This is likely to be a braking force, and that's why we will take a negative. So we can say that now force is given by mass times acceleration, 0.5 times negative 20. And this will give us negative 10 newtons. When force is negative, it talks more of the direction of the force. Remember, force is what you call a vector quantity with both direction and size. Therefore, negative 10 means a force of 10 in the opposite direction. So technically, we can say that the force is equal to 10 units. 10 newtons, only that now this force is working in the opposite direction. It's a braking force, in other words. Part B of the same. A player throws a tennis ball upwards and catches it at the same point of projection after 4 seconds. Sketch a velocity time graph to show the motion of the ball. Velocity time graph. Let's do this first. We need velocity in time along the x. So we need velocity here and time in seconds. Velocity in meters per second. Now, what you're supposed to know is that a certain player is throwing a tennis ball upwards and catches it at the same time. When the ball is being thrown originally, it's usually having a certain value of velocity. Then this velocity now starts immediately decreasing. This is a vertical projection. Therefore, we expect decrease in velocity. So if we start from a certain value of velocity, this velocity shall decrease until it is 0. Then immediately it arrives at 0. The same velocity now starts increasing again as the body comes down to the ground. It starts accelerating due to the force of gravity. Actually, according to the equations of linear motion, you discover that when an object has been projected upwards, it decelerates, eventually arrives at 0, then it turns the direction and starts coming down and eventually begins accelerating again. By the time it is landing on the ground or at the point where it was released, it does so when it has already acquired again the velocity it had been thrown up with. So if you throw a ball upwards with a velocity of 10 meters per second, for example, it starts decreasing until it hits zero. Then it starts coming down and accelerates again until at the time you catch it again, it will be at 10 meters per second once again. So it lands with the same velocity that you threw it up with, meaning that now this particular velocity starts increasing again. Once it is increasing, we are supposed to know that the same velocity now is in opposite direction. So that's where we will take it. You discover that by the time it's ending the journey, by the time the player is catching this particular object, it is at a negative velocity or at a value of velocity negative, but equal to the original velocity, which was positive. The velocity was thrown up with. So the reason I've taken it to the negative side is because velocity is a quantity that has direction. It is not the same direction. So there is no way we could say this object after reaching zero, it goes back to the same position. No, it's not going in the same direction. The direction is opposite. So it might be the same value of velocity, but now that it is in the opposite direction, then you change the side of the axis where the velocity is going to be sketched. So this is what the examiner expects now. Part C. Two trolleys, A and B, of masses M1 and M2 are moving towards each other on a frictionless horizontal track. Trolley A is moving with a velocity U1, while trolley B is moving with a velocity U2 in the opposite direction. The trolleys collide head-on elastically. We'll be talking about elastic collisions and also inelastic collision. Part 1, state the law of conservation of linear momentum. It should be known that for a system of colliding objects or bodies, the linear momentum is conserved, provided no external force that acts on the system. So the linear momentum of a system of colliding bodies is conserved or is preserved, provided no external force acting on the system. So as long as the system is not interfered with by any external force, after collision, linear momentum is usually conserved. Write the equations for the conservation of momentum for this case. So for the case above, we are saying that momentum before collision should be equal to momentum after collision. Before collision, we can talk about the first body, M1, moving, the first body, which is a trolley A, moving with the velocity U1, plus for the other one, though in the opposite direction, but it has a momentum of M2, and its initial is its initial is U2, like that. This one should be equal to momentum after collision. But look at this. The collision is elastic, meaning that once they collide, each body moves in its own direction. Each body moves with its own direction. Therefore, we can have the first body moving. They don't combine. Bodies don't combine when collision is elastic. Therefore, the first body moves with final, and also this second body moves with its own final velocity. So momentum is usually conserved. Look at the second case. State one characteristic of elastic collision, the one we are talking about here. Okay, characteristics are many, but the basic point is that kinetic energy is conserved. Kinetic energy is conserved. Linear momentum is also conserved. Linear momentum is conserved. And again, you should know that bodies do not stick together after collision. The bodies do not stick together. The bodies separate. That's another property. Actually, it's the one of the properties that distinguish elastic and inelastic collisions. Here we say that the bodies do not stick together after collision. Number 13, part A. State Archimedes principle. So when we are studying what we call floating and sinking, we say that when a body is fully or partially immersed in a fluid, let me write it as I dictate the law. When a body is fully, can also say wholly, or partially, can also say partly, immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. Because for a body to be immersed, whether fully or partly in a fluid, it has to displace some fluid. Now, this fluid displaced is having some weight. This weight is what we are saying that is equal to the upthrust acting on the object. Yeah, equal to the upthrust acting on the object. Part B. The figure below shows a block of mass 25 grams and density 1,000 kilograms per meter cubed, submerged in a certain liquid and suspended from uniform horizontal beam by means of a string. Look at that. There's the string, 25 grams inside liquid. Then what are we told? That a mass of 20 grams suspended from the other end of the beam puts the system in equilibrium. So the system that you can see is now in what we call equilibrium. Determine the upthrust force acting on the block. Upthrust force acting on the block. Let us first apply what we call the law of lever, or rather the principle of moments, that says for a system in equilibrium, sum of clockwise moments about a certain point is usually the same as sum of anti-clockwise moments about the same point. So these 20 grams can be converted to weight, and weight is usually given by mass times G, mg. So we'll be talking about m, 20 over 1,000 times the value of G, which is 10. Remember, in the instructions on the cover page, you were told to apply G as 10 that way. So from this now we can say clockwise moments are caused by the 20 grams mass. So force times distance, 20 over 1,000 times 10 times the distance there from the turning point to where the force is acting, 0.1, equals to, on the other side, we have a known upthrust. Okay, we have a known apparent weight. This apparent weight of the block is the one bringing equilibrium. So we multiply it by distance. Distance in this case is 0.16. So we can get the apparent weight. 20 by 10 over 1,000. Then we divide by 0.16. You see, this gives us 1.25 newtons. This is the weight now. This is the weight which is causing equilibrium in this particular system. We can also get the real weight of these, whereby we need mg 25 times g, but this one should be made SI units. So yeah. But wait a little bit. When we were working out 20 times 10 times 0.1 over 1,000, that should have given us 0.02. Then we divide by 0.16. Now this should give us, sorry for this, I had forgotten 0.1. So this should be 0.125 newtons, because I almost realized actual weight or real weight is becoming less than the apparent weight we had computed. So now from here we can say 25 to 50 over 1,000, 0.25 Newton. Yeah, this is what I wanted now. With this now, we can say that upthrust is the difference between actual weight and apparent weight. So 0.25 minus 0.125. This will give us 0.125 newtons. So this is now the upthrust experienced. The body is having 0.25, but when it has been immersed in water, it weighs 0.125, which means there is an upthrust acting on it. And we have computed the upthrust. Yeah, the upthrust is properly computed. We proceed to the next part of the same question. We determine the density of this liquid. You see now the liquid which has been displaced, we know its weight according to the upthrust and according to the statement of the Archimedes principle that upthrust experienced equals to weight of the fluid displaced. Remember, this block is having a mass of 25 and a density of 1 gram per cubic centimeter, which means we can find its own volume. What is the volume of the block? You know, density equals to mass over volume, right? Meaning that volume equals to density over mass. So a density of 1 out of 25, that will be volume, 1 over 25. So volume of liquid equals to 1 over 25. Volume, this volume of the block, which was placed in water. And it's good for you to know that volume of the block equals to volume of liquid which was displaced. So we have volume and we're also having the weight. The weight is equal to upthrust. The weight equals upthrust 0.125, which means we can get mass. You divide this by G, we get 0.0125 kilograms. Then we can say the mass can also be written as 12.5 grams. So this is the mass of liquid that got displaced. Then the volume of the liquid that got displaced must be equal to volume of the solid causing the displacement. Yeah, causing the displacement. So now from that, now we consider density according to this formula is given by mass times volume. Mass times volume. So let's talk about 12.5 divided by 25. 12.5 divided by 25, giving us 0.5 grams per cubic centimeter, which can otherwise be written as SI unit, like that. So this is now the density of the liquid. Yeah, density of the liquid, properly calculated. Part C of this system. Look at part C. The system in the figure below is at equilibrium. We have a gas and a solid. State and explain what may be observed as the temperature of the surrounding is decreased. So when you decrease the temperature, remember the gas is they are both going to contract, yes, but the gas will contract at a faster rate. And if it contracts at a faster rate, then we have the position of the COG of this gas now shifted towards the center. And hence, this solid will be able now to swing the system in a clockwise direction. So the system turns in a clockwise direction. The system turns in a clockwise direction. So the gas contracts at a faster rate. The gas contracts at a faster rate, shifting its COG to the right. Hence, the solid will swing the system downwards. So the solid will swing downwards. Number 14, which is on gas laws. Let's look at the question. We are told to state one condition for Charles' law to hold. For Charles' law to hold, it's one very good for you to know how the Charles' law states. And we say that for a fixed mass of a gas, we say that volume is directly proportional to the absolute temperature, yeah, when the pressure is kept constant. I don't know whether you've heard that. For a fixed mass of a gas, the volume is directly proportional to the absolute temperature if the pressure is kept constant. So conditions for Charles' law to hold, one is that pressure must be kept constant. Pressure is kept constant. And again, we have another condition, mass must be fixed. You know, as you carry the experiments on Charles' law, you can't keep changing the pressure, the mass of the gas anytime. So both mass and pressure are kept constant during the experiment. Then part B, the diagram below shows setup used to verify Charles' law. Use it to answer the questions that follow. So we can see the setup here, a thermometer, a star rubber band, which is tying together some sulfuric 6 acid, some trapped air, a water bath, a scale. Then look at part A of the question. It says the reason why sulfuric 6 acid is used as the index. You know, sulfuric acid has several purposes, and in this experiment, we usually say that the sulfuric acid is one of the drying agents to the gas, because the gas used here must be dry gas. Therefore, sulfuric acid acts as a drying agent to the gas. Acts as a drying agent. Drying agent for the gas. Again, sulfuric 6 acid, you know, it's an index. Therefore, that index will be used as the reference point to examine the behavior of the air column. So when the air has expanded, we will observe the column of the sulfuric acid index. When it has contracted, that is what we shall refer to. So it is used as the reference point for the volume of the air. So it is the reference point, the reference to the behavior of the air column. Because air is colorless, for us to know when it has expanded, we check the column of the sulfuric acid. List 2 measurements taken in the setup. As a student, when you get a question like this, listing measurements, you know, there are some keywords that you're supposed to underline. Measurements taken in this particular experiment. You look at the apparatus which have been involved. For example, you can see a thermometer. Then you can see the sulfuric acid index. Therefore, from the thermometer, what are we able to measure? Temperature using the thermometer. Temperature using the thermometer. Then else that we're supposed to measure is air columns. Air columns using the sulfuric acid index. You follow the sulfuric acid index for you to know the column of air, how the air is behaving, for you to know when it expands, when it does not. Then part 3, explain how the measurements stated in Roman 2 can be used to verify Charles' law. So you tabulate, or first you can record initial temperature and also the initial air column. Initial air column like that. Then you see there is a source of heat here. As you continue heating, you tabulate the values of temperature with corresponding values of air column at some intervals of time. At some intervals of time. Then after you've acquired some good data, now you can plot a volume against temperature now. Volume against temperature. Then we say that a straight line shows that Volume is directly proportional to the absolute temperature, or rather temperature. And hence, you will have verified the Charles law. Now, a balloon has a volume of 2.5 liters at 27 degrees Celsius. Determine its volume if the temperature is raised to 127 degrees Celsius at a constant pressure. In other words, this is according to Charles' law now. So we should be able to know that volume 1 out of temperature 1 gives us the same constant as volume 2 out of temperature 2. So what is volume 1? 2.5. Temperature 1, we convert it to absolute temperature. So 27, we add 273 to convert it. That gives us 300 equals to volume 2 unknown out of temperature to 127 plus 273, get 400. So now we can get V2 as 2.5 times 400 out of 300, giving us exactly, okay, let me just recompute again. I'm using 2.5 times 400 out of 300. This gives us 3.333 liters of air. So that is it. Thank you so much for following. Subscribe to this platform. Share to invite your friends.